Well, hello everybody. We'll wait just 1 or 2 minutes to allow the people who are entering the webinar, and we'll start. All right, I think we can start now. So first of all, good morning, good afternoon, or good evening, depending on your time zone. Welcome to this new webinar from the Trevor Platt Science Foundation. As you know, this is an international organization dedicated to capacity building in science, research, and education related to our oceans, working towards stewardship of our planet for future generations. Today's webinar is one of the capacity building activities of the Foundation. So before introducing our distinguished speaker from today, a couple of instructions. As you will see, your microphones are off. Please write your questions on the Q&A box, not in the chat, and we'll get to them after the talk. So now it's my honor to introduce our speaker today is Dr. ZhongPing Lee. He got his PhD in 1994 from the University of South Florida. Dr. Lee is a fellow of the Optical Society of America and currently a Tang Chi Feng Chair Professor at the College of Ocean and Earth Sciences of Xiamen University in China. Dr. Lee's main research interests are in optical oceanography and ocean color remote sensing. He led the development of the widely used quasi-analytical algorithm and the hyperspectral algorithm for processing both optically deep and shallow waters, along with various applications of satellite ocean color products. His theoretical work of 2015 on the interpretation of the Secchi disk depth for underwater visibility overturned about 70 years of classical theory adopted by the ocean optics community. He has authored or co-authored more than 200 peer-reviewed articles in mainstream scientific journals with more than 27,000 citations by Google Scholar, and is a member of many science teams for ocean color remote sensing. His talk today is on the heating of the upper ocean by solar radiation. Details matter. So, Dr. Lee, the floor is yours.
Thank you, Vivian. Thank you a lot for the invitation. And it's a great honor to be here to exchange thoughts, ideas about ocean optics and ocean color remote sensing. And yes, as Vivian said, good morning, good noon, good evening. So thank you all for participating in this great event. Okay, now I will start with my presentation. And so I will turn off my video, so then that may be easier, smoother for the presentation. So can you see my presentation? I think that's all right, right?
Yes, it's fine. It's fine.
Okay. All right, I will start. I will cover these 5 aspects, some basics, some common parameterization of the propagation of solar radiation, and the impact, and also the impact of vertical resolution on the heating effect. And at the end, I will give some conclusion. As we all know, sunlight penetrate the water or place the ocean, can get into the deeper depths, like say for the ocean, it can get to 200, 300 meters. Actually, for the ocean, at the deeper depths, the pretty much the main heating source is from solar radiation. Yeah, at some mid-ocean ridge due to volcanoes, they may have some kind of a heating source from the sea floor, but 99.9% of the heating source is from the sun because it can penetrate into the deeper ocean. So that's a fact. We all know that. You realize this, so there have been many studies to see how the ocean substance in the ocean change the heating, and also how the heating effect kind of feedback to the atmospheric system. So like in the, let me see if I can get a pointer. Yes. So as early as kind of more than 40 years ago, there have been studies on about the heating of the ocean by different water types, and a big contribution from SUBA that was also 30-some years ago is a biological control of temperature by the biological, by the plankton and other constituents in water, how that will impact the heating, and then the whole atmosphere and ocean system. And subsequently, there have been many, many studies in this aspect. So I just list a few here. Actually, for the solar radiation, a majority of that reaching the Earth's surface is between the 300 and 2500 nanometer range, with most of that centered around the 460, 470 nanometer. These are based, as we know, these are the visible range, okay, of the solar radiation. And sometimes we also call these as shortwave solar radiation. And it's this part, the visible part, that can penetrate deeper into the depths. And for the solar radiation, it propagates from the surface to deeper water, no matter it's kind of clear water or really turbulent water. It attenuates quickly, okay, quickly. Sometimes we call it exponential, but many times actually it is super exponential because it attenuates very fast near the surface. If we expand this to spectrally resolved solar radiation, say as shown here, here is about 360 nanometer all the way to 700 nanometer. Okay. So with the increase of depth, we see the attenuation of the solar radiation quickly. As you can see here, it's in log scale. But another important factor is that the longer wavelengths, it attenuates much faster than the shorter wavelengths. This is a very important feature of the solar radiation, how it propagates from the surface to deeper depths. Okay, and so in general, because of this feature, we generally express, we call this ED, the downwind spectral irradiance, as a function of ED at the surface. Okay, then it has an exponential function of kd times z, and this kd is called the diffuse attenuation coefficient. Z is the depth. When we're talking about a narrowband, say per nanometer, normally we can assume and we can take kd as a constant vertically. Okay, so that's a general feature for the attenuation of solar radiation in the upper water column. So here are the examples of this diffuse attenuation coefficient, the spectra. This was presented in almost 30-some years ago by Maria. Okay, here is the shorter wavelengths, here longer wavelengths. As you can see, the longer wavelengths in general, this KD is much stronger than the KD in the shorter wavelengths. Basically, these are the open ocean waters. These are kind of coastal or nearshore waters. So in order to estimate EDZ, the spectrally resolved solar radiation, we need both ED0 and the spectral KD. But ED0 is basically determined by the location, time, and atmospheric properties. So that pretty much has nothing to do with water properties. For the solar radiation in water, a key parameter is this KD, especially spectral KD. Based on radio transfer, this KD is a function of A and BB. A is the absorption coefficient, BB is the backscatter coefficient, with M0 and V are the modeling parameters. So after we know A and BB, we can calculate KD, a spectrum. Okay, you said not simply one wavelength, as here shows with the black is the profiling system measured the spectral KD. The green is remote sensing estimated spectral KD. As you can see, for two different cases, the estimated KD match the measured spectral KD very well. So in that sense, you really have a like space by a hyperspectral sensor, then we can get hyperspectral KD for the global ocean. But for numerical modeling, okay, because of the limitation of computer powers, normally we don't take spectral KD. Rather, to break up the shortwave solar radiation into two bands, okay, two big bands or wide band. One is for the visible, basically 350 to 700 nanometer. Another is basically for those solar radiations after 700 nanometer. Then for the two separate wide bands, we have visible. Visible has a K visible, because that's the attenuation for the visible band, and the KIR for the attenuation of the IR band, infrared. Okay, and now, okay, while KD, as I mentioned a moment ago, while KD we need concern the depth independent, KVIS and KIR are depth dependent. That's it's a key difference between KVIS and KD. So here are numerical simulations from hydrolite. As you can see, for three different environments or cases, this is K visible. Okay, this is K visible. As you can see, near surface, the K visible is maybe about 0.2. Okay, 0.2. But at the deeper depth, here is about 0.1. For this case, okay, near surface is about 0.2, but at deeper depth, like 40 meters, that's about 0.06. That's about 3 times, okay, just for the surface range, the change of 3 times or 2 to 3 times for the K visible. So even for homogeneous water, these are homogeneous water, K visible varies significantly with depth. The reason is, okay, because the longer wavelengths, the red wavelengths, it attenuates very fast near surface. Okay, so those are absorbed near surface. So that's how the near surface is K visible. It's much higher than deeper depths. For deeper depths, there is no photons to attenuate anymore. So basically, it's the blue photons. So blue photons for oceanic water, the attenuation is low. So at deeper depths, it's lower values. at the near surface, it's much higher values because of the spectral narrowing, okay, with the increase of depth. So if we assume KVIS as a constant vertically, then you can imagine, okay, near surface, there will be, we use a much smaller number, so it'll be kind of a more photons will be returned at near surface. But use a higher values for deeper depths, so it'll be lower, okay, there'll be more solar radiation, visible solar radiation near surface, but much lower compared to truth, okay, at deeper depths. So that will be an impact if we use a vertically constant KVIS. So from the numerical simulations, we can model the two wideband attenuation and these two formula. Here, this is for K infrared. Here is for visible. As you can see now, the K visible and the KIR, it varies with depth and it varies with the solar lattice angle. Here, the IOP basically represents inherent optical properties, or basically it's a representation of changing water properties. So now we see KVIS and the KIR both are depth and sun angle dependent. That's the basic nature of these wideband attenuation coefficients. Okay, in practice, in numerical simulations, because of the limitation of computation power, so normally we don't use, or the modelers don't use spectral resolved form. They rather use wideband based spectral integrated form. For instance, this E solar radiation expressed as a basic integration from lambda 1 to lambda 2. This number lambda 2 can be between 350 to 2500 nanometer, or between 350 to 700 or 1000, as I talk more. Okay. So to propagate this ESR from the surface to deeper depths, normally there is a transmittance defined, the TR, the transmittance of solar radiation. Okay, but it's more integrated, spectral integrated solar radiation. The most commonly used model by modelers is this Paulson-Simpson model, 1977. In this model, this TR for solar radiation is broken into two exponential terms, with Z for depth. R is a constant. Normally, it's about 0.62. And then this cosine 1 and cosine 2 are basically constants, which are water type dependent. Okay, you just it's based on the journal of water type. Given water type, it gives us a number of cosine 1 and cosine 2. So then for big range, big area region, okay, basically it's the same transmittance used in the model. Okay, as we know, water properties actually change frequently and strongly from one place to another. So this cosine 1 and cosine 2 should not be a constant, okay, spatially. But anyhow, this model, this PS77 model, has even till today still used widely in ROMs, HICOM, and many other systems. As we know well now from ocean color remote sensing, we can get chlorophyll concentration of the global ocean. So here you see the chlorophyll based water properties change a lot spatially from one place to another. So we cannot say use the same cosine 1 and cosine 2 for this big area or region. So in order to use this chlorophyll information, the models developed based on chlorophyll. Okay, and this model KVS as two constants, K water and Kc, and a function of chlorophyll. And this model is also used in many numerical simulation studies. It can be dated back to Smith and Baker, 1978. Okay, in this system, the two model parameters, Kw and Kc, are kept as global constants. Not only change location with location or not or places, but also a constant vertically. Please remember that. Okay. But in this system, they do not okay, based on this system, this KVS will be a constant vertically. Also, it does not vary with some angle. But I just showed moments ago, KVS, because it's spectral integrated attenuation, this KVS should be a function of depth and should be a function of some angle, because that basically is a change of the standard path of the photons. So as you can see, this model is not consistent with radio transfer, nor is supported by algebra. I will show you why it's not supported by algebra. Okay. As we say, for the visible, the solar radiation is the integration of the say 400 to 700, and the ED lambda at the depth is ED 0 and times this exponential function of E minus KDZ. Then EVSZ will be an integration of EDZ. Put this dependence here, then it will be integration of ED0 lambda times E minus KD, blah, blah. And the transmittance is defined as EVSZ divided by EVS0. Then this TR EVSZ will be this integration divided by integration of the surface. Now you can see this ED0, okay, because it's integrated with this attenuation, it could not be cancelled out. Okay, and this whole thing will depend on these steps. So if you keep KVSZ as a constant, this ratio will not be able to equal to E minus KVSZ. Mathematically, that's what I mean. Algebraically, by algebra, this could not be derived. Actually, this is not a new thing. Back to 1988, Andrew Morel specifically says, if you wrote it this way, K par or KVC as KW plus KCZ, then this KW will be a function like this, okay, which is similar as I showed moments ago. But for this function, then this K water Z will impossible be a constant. This K water 0Z will depend on the Z used or the range of Z, or basically depends on the thickness of the layer. So Morel summarized that, in other words, an expression like this equation, which is supposed to solve a problem by a simple way, conceals other much more complicated problems. As shown here, this algebraically could not be derived, and this is not supported by radio transfer and not supported by algebra. Okay. We can also use data to evaluate this system. Okay. We use the measurements in the Pacific Ocean and the many measurements in nearshore waters. Okay. And we can estimate a chlorophyll from remote sensing reflectors, and we can also estimate theoretical optic properties from a QA algorithm. Then we can compare the estimate transmittance versus measured transmittance. On the left is based on this chlorophyll simple model. Okay. On the right is based on the inherent optic properties and taking that key VIS as a function of depth and the angle. So as you can see, if you use a simple chlorophyll-based model, the mean absolute percentage error is almost double of that by IOPs. So this demonstrates that the simple chlorophyll model, yeah, it's easy to calculate, to implement it in numerical simulation models, okay, especially in the dynamic ocean circulation models. But because that model is not consistent of radio transfer and is not supported by algebra, there are much more errors or uncertainties to estimate in the estimated transmittance. Recently, we also used many algo data to evaluate this. Here on the left, it's a chlorophyll model. On the right, is using IOPs. Again, we can see the performance of using IOPs, especially treat KVS as a depth-dependent variable. It performs much better than simply using chlorophyll. Okay, in short, to determine, to estimate the accurate short-wave solar radiation at depth, we should be very careful about spectral range. We should be very careful about the attenuation coefficient, especially its vertical variation. We should also taking care, okay, we should also taking consideration of solar zenith angle. The traditional approach of KYS as K water plus K times chlorophyll, which has no depth or angle dependency, this one is not consistent with radial transfer. Okay, that should be something really kept in mind for modelers, especially circulation modelers. Then people ask, so what? Okay, yeah, you can get a better solar radiation model, so what? See, we're trying to address this question by ourselves. We suppose the modelers to do this, but since they are not interested in this, then I get a student to do this. So we're trying to see how the transmission scheme, okay, will impact the dynamics. We picked 6 locations, 1, 2, 3, 4, 5, 6, from open ocean, very blue waters, to near shore, quite turbulent waters. So these are the remote sensitive reflectors of these 6 locations. And you can see, okay, basically this is location 1. It's a typical, okay, blue ocean water, remote sensitive reflectors. Here is a coastal, quite turbulent or high chlorophyll waters. And for the same 6 locations, it's the same RS. Okay, we have the input, then to get a chlorophyll, and then to get the ILPs. From chlorophyll to get ILPs, then we can estimate the transmitted. Okay, here is the comparison. Here is station 1, here's station 2, 4, 3, 4, 5, 6. Okay, as you can see, there are 4 models. One is the Paulson-Simpson 77, that's the black curve. Then O is for Ohm-Hansen, that's a blue curve. M is for Masugudi, this red, okay, it's chlorophyll model. Ohm-Hansen is chlorophyll model. Then this green is L05, it's our IOP-based model. Okay, you can see, okay, for the 6 stations, from blue water to nearshore coastal nearshore water, where high chlorophyll water, the estimate transmitters differ a lot. Okay, and actually the closest one is between the D05 and the Paulson-Simpson for many for this for this, but not for this steps. Okay, not for this step. This x-axis is the log of the transmitters. This is depth. Okay, so here is basically this is close to surface, almost 0 meter. Then it's 0.1. This 1 meter, 10 meter, 100 meter. So you see, for Paulson-Simpson, okay, here I can see at 1 meter, its attenuation it's much smaller, okay, than the other models. Other models still have, see here is 10%, 20%, 30%, 40%. At 10 meters, yeah, here's 10 meters. So 2 or 5 meters. Other models have about 20, 30% of solar radiation, short-wave solar radiation, but the Paulson-Simpson is just about 20%. So here shows the differences. Then we use this to run a 1D simulation of ROMs. Okay, all the other components are kept the same, except the transmission scheme. Basically, use 4 different transmissions. Here are the results of these 6 stations. Here are the temperature profile. Okay, temperature profile for station 1. Here, temperature profile for station 2, station 3, station 4. Okay. For this chart, it shows the difference between other models versus Paulson-Simpson. Okay, but here again, this is for station 1, this is for station 2. Let's zoom in to look at station 1. Here is the vertical profile. Here's the difference. Now you see, at 20,000 upon 30 meters, this Masugudi 02, that's based on chlorophyll. The temperature can differ by about 0.6 degree. Okay, and for this one, the on Hansen, okay, then it's the opposite. At about 30 meter deep, then the temperature is lower by about 0.2 degrees. For the surface, okay, say surface temperature, then the Matsugudi has more, basically has a lower surface temperature by about 0.1 degree, and then the on Hansen is about higher temperature at the surface, about 0.2 degree. D05 versus Paulson Simpson at the surface is about the same, but at deeper depth, then it's about 0.1 to 0.2 degree different. Here is a time series for a year. Okay, here's the January to December, station 1, station 2, station 3. These are the temperature, sea surface temperature time series. Again, here are the differences, okay, for the different months. Again, you see for the Paulson-Simpson, these are a difference between the other models versus the Paulson-Simpson. Again, for the Matsugudi, at say September for station 1, the temperature is lower by about 0.6 degrees. And on Hansen, it's at December, it's higher by about 0.1, 0.2 degrees. Based on the IOPs, generally, for the summer to 4 months, it's lower by about 0.2, 0.1, 0.2 degrees. This is for station 1, station 2, station 3. Even for, so you can say, generally speaking, these transmission models can cause quite big differences compared to Paulson-Simpson on the sea surface temperature. Then we look at the mixture depth. Again, here are the time series for a year from January all the way to December. Okay. Here are the differences between other models versus Paulson-Simpson 77. Again, station 1, station 2, station 3. Again, you see, okay, it also will impact the mixture depth. For the Matsugudi model, which is based on simple chlorophyll, the depth, okay, here is the minus means deeper, okay. Minus the mixture depth will be deeper. The Matsugudi depth at this May will be deeper by about 30 meters. And for the IOP-based model, and also the mixture depth will be also for station 1 deeper, sometimes by 10 meters, sometimes by a few meters, then station 2, station 3. So all these are talking to that there's a significant difference in dynamics due to this change, okay, or using of different transmission models. That's not surprising because, as I mentioned at the beginning, for the deeper depths, solar radiation is pretty much the soul is the only heating source for the deeper depths, the 50 meter, 100 meters. So that because different the heating, then the dynamics, the mixing will be different, and then so on. The dynamics, the mixture depth will also different. In addition to that, actually, the different transmission scheme can also impact the prediction of the heat content and the hurricane intensity. But because of the time limitation, I will not talk about details of how this shows. But if you are interested, you can check this paper, okay, about the impact to the heat content and the hurricane intensity due to these different schemes on solar transmission. So those are about numerical simulations. We also talk about vertical resolution. Yet, before we talk about the modeling of different schemes to do the transmission, here I will also show the vertical resolution and other details in the dynamic modeling. As I mentioned in the beginning, the solar radiation attenuates super exponential with increased depth with this kind of pattern. But in numerical simulation, because of the limitation of computation, we cannot take such high vertical resolution. Okay. Instead, in order to get computation efficiency, Normally, it's taken by different slides, okay, or different layers. Here's layer 1, here's layer 2, here's layer 3. For each layer, it's assumed it's the same solar radiation for each layer. Okay, so here for this layer, it's kind of like the sun. It's heating, okay, sideways. For this layer, the smaller sun heating sideways. For the third layer, it's an even smaller sun heating the sideways. So this layer, it's heated. The whole layer heated uniformly. But as I showed with this profiling, actually it's not. In reality, the solar radiation, okay, attenuates very fast. So the upper layer is heated much more than the lower layer. So then we'll see, okay, how this kind of treat each layer heated uniformly, how will that impact the result or impact the vertical dynamics? Especially in many studies, the first layer is a mixed layer. Then we run some numerical simulation again with ROMs. We took 3 different resolutions. One is with 5 layer, okay. Another with 10 layer, another with 30 layer. 30 layer, as you can see, will be really much highly resolution vertically. When for n equals 5, the first layer will be simply the mixed layer. So it's here, okay. This is initial temperature. This is the first layer. These are the results after run of 20 days. So you can see for this is the difference, okay, the difference. For this red, it's for 5 layer minus the 30 layer. Basically, it's a low resolution minus the super resolution. This is for the x-axis. Red is for n equal 5, and the blue is for n equal 10. Equal 10 minus 30, okay. Red is for 5 minus 30. Now you see, okay, for near surface, when n is 5, the surface, the system temperature is lower than the super resolution. Here is 0, here is 0.5, here is about 0.8. So simply treating the surface, treating the vertical, the mixed layer as one layer, okay, instead of multiple layers, the system temperature become lower. That's because it's more photons. It's assigned to the lower part of the layer with less photons assigned to the near surface part of this layer. So the heating effect is lower for near surface, but with more photons to heat the lower part of the mixed layer, so get the temperature getting higher. Here's a similar thing, okay, for n equal 10. At the deeper depths, then you get a higher temperature compared to the super resolution. Then from this, we can integrate the heat content, okay, of these 3 different resolutions. For this black is for the super resolution with n equals 30. This is for 10 layers. This for 5 layers. Because of the vertical resolution, or the different vertical resolution, the coarse resolution have more heat contents in the water column compared to more higher resolution. This is for the wind speed as 0, okay, at 0. Then if we increase the wind speed, then we increase mixing, then this effect, as you can see, because the increase mixing, then the effect is it's minor, okay, it's minor. But still, at a deeper depth, the temperature from the lower resolution will be higher than the higher resolution, okay. Here is the heat content, okay. The heat content also for lower resolution has more heat contents, the higher resolution. So these are numerical simulations. We also did some laboratory experiments to check this. Because here we have a light source put on top. Here is a tube, okay, it's a coarse tube, okay. It's a coarse tube with 50 centimeter long, which has pipe waters. Here's the same tube, okay, same tube, also same length, 50 centimeter, but we had the same heat source, but put at the bottom. Okay, here kind of same as the solar heating from the top. Here is the same as the solar heating from sideways. Because when it's heating from the bottom, the heated water will quickly going up because of the reduced density. So the mixing will happen instantaneously. So it's kind of simulating the heating the tube sideways. So here are the results. When the heating is from above, obviously we'll get stratified layer because most of the heating source is near surface. So near surface get a much higher temperature. Okay, after about 90 minutes. Okay, 90 minutes. This profile is measurable every 10 minutes. This is heating from above. This is heating from below. As you can see, the water column is generally uniform. It's kind of, as I said, kind of like heating the tube sideways, because heating from the bottom, the mixing happens instantaneously. So we get vertically uniform, nearly uniform temperature profile. Again, we calculate the heat content in the tube. So here is the heating from above, kind of high resolution. Here is the heating from below, kind of low resolution or heating sideways. Again, low resolution have more heat content in the tube compared to high resolution. This result is consistent with the numerical simulations. Okay. So to conclude, for spectrally integrated solar radiation, the attenuation coefficient is a strong depth-dependent variable. Okay. This and it's also a function of psi angle. This is a fundamental from radial transfer. If we take K as a constant vertically, it will result large errors in the estimate solar radiation at depth. Okay, it will in turn affect simulated temperature profile, as I just showed a moment ago with round simulation. Okay. So solar radiation attenuates strongly with depth, so especially in the upper water column. Then treating the mixed layer as a heated uniformly, kind of like I just mentioned, the heated sideways, that is not consistent with reality, because in natural water, okay, in the Earth system, the sun is on top. So near surface is heated much more than deeper depths. But however, if there are strong winds, then the mixing is so strong, this solar radiation, this vertical sort of difference, then play a minor role. Okay. So all these details on the attenuation coefficient, how it varies depth, on the vertical resolution of the numerical simulations using the model, all these we think matters, okay, for the modeling, or simply for the heating of the complex ocean atmospheric system by solar radiation. Okay, I'll stop here. Thank you very much. And let's see if you have any questions or comments.
Thank you very much, Dr. Lee, for a very interesting and provoking talk. And let's see the questions that we have here. Okay. People are shy, no questions so far. So I will take it. So I will take advantage. Of course, I'm not an expert in this subject, but I was quite intrigued because I always thought that there is this issue with, I'm more of an in situ measurement person, and always with the models you have to somehow parameterize and take some assumptions. So of course you get a little bit further from reality, and as you show here very well. And there is always this concept as the mixed layer being perfectly mixed, and as you show us here, that's not true and can make very strong differences. So I enjoyed your talk very much. That's what I wanted to say.
Thank you. Thank you. Yes. So think. Let's take an example in the tropical. In tropical, in the summertime, when there are less wind, when there are less wind or mild wind, then that mixture, say maybe the thickness is 20 meters. Then from that on, it will still continually be heated by the solar radiation. Then in the subsequent days, that heating, because of low wind, then that heating, most of that heating will happen at the near surface, with most photon near surface, less photon at deeper part. So that mixed layer will be re-stratified to near surface.
Yes. Yeah, I was
wind
thinking
play
about...
a big role, but depends. Yes.
No, I was thinking about
ahead,
that. Yes, that exactly as you just said, that that will be especially important in the tropics, where you have very calm weather and very strong incident irradiance. And as you showed, there is this problem very directly on the surface that with the model you are underestimated actually the heat, and a little bit further with depth you are overestimating it. So that would be an issue in the very thin layer at the top and down there.
The two different aspects. One is about how to parameterize the attenuation coefficient. Another aspect is how to divide the layer. If a model simply you take the mixed layer as one layer to heat, instead to divide the mixed layer by many different layers, then it will assign less photons to near surface, then more photons to deeper depth, because it uses average K. That average K, it tends to make less, basically, it averages the photons out, not average K. It averages the photons out by placing more photons at a deeper layer and assign less photons at the upper layer or near surface. As a result, then the near surface will be less heated, then deeper layer will be more heated. So deeper layer will get a higher temperature. That's the reason. That's because of the vertical resolution, not because of the parameterization of the K.
Yes. Yes, I understand. So here we have a question from Milton Campbell from Brazil. And he asked, have you assessed the role of different optical water types in the simulations of the profiles?
I'm trying to find the question. Where is the question? Oh, okay. Have you asked the role? Assess the
different
role
optical
of
types, I
different
guess.
water types.
Yeah.
Oh, yes, we have in one. Hi, Milton. Happy to see you online after we met in IOCS. So here, in this case, is different water types.
Okay. Yes, that's right.
There are 6 different water types. So basically, your number 1 is very blue oceanic water. To number 6, it's kind of quite a turbid or high chlorophyll water. That way, yes.
Yeah. Yeah, because I don't know, I'm maybe wrong, but I guess that if you have a very complex, very turbid water where light attenuates fast, maybe the error would be less because the effect of the heat will be closer to the surface, or I'm wrong?
Yes, you are right.
Okay.
You are right. But the thing is, in this case, if it's based on chlorophyll, that K based on chlorophyll could be wrong a lot.
Of course,
that attenuation could be wrong a lot.
Yes. Yes. Again, we go to that in the very blue waters, in the tropical ones, is where the error will be probably higher because of the two effects, the type of water
and the... Yes, you are right. Because for blue waters, then the vertical variation of the K play a bigger role.
Yeah, and on top of that, in those waters probably is where you have more calm weather as well.
Yes, yes.
Also,
I see. Milton has another question about the cystic. Yes, when you have, as I showed later, you will have really strong wind. Then this no longer matter much because that vertical mixing can kill the optics. Yeah. See, like I say, in the polar region, the wind is so strong, it's constantly mixing and mixing and mixing. It's all cold water. The solar radiation, the role of solar radiation, or especially the parameterization, is no longer a big issue.
Yeah, yeah, yeah. The wind really helps to homogenize everything.
Yes, yes, yeah. Physics is still the king.
Yeah, yeah. Sometimes it's this issue of where is the surface. Sometimes you can take samples right at 0 meters, 2 meters, 5 meters, or 10 meters, and will be the same or will be very different.
Right.
Yeah.
Thank you, Milton. Thank you.
Yeah. Thanks. So I don't know if there are no more other questions. Let's see. There are some comments here. Everybody says was a very interesting conversation, and they enjoyed the presentation.
Thank you all.
So if there are no more questions, let me thank you very much, ZhongPing Lee. It was a pleasure to have you with us. I know we are very busy and it's almost dinner time for you, and you're here.
And this is a mental dinner. Very good.
Okay.
Yeah.
Thanks very much. Yes. And also thanks to all the members and students who joined us today, and especially to the Air Center, Patricia Kwan, for hosting the transmission. And we'll be in touch and hope to see you soon in the next webinar. The next, I can just send a quick announcement. In January, we'll have Dr. Subrata from Bangladesh. So we hope to see you here. Okay.
Okay.
Bye, everybody.
Thank you.
Thank you.
Okay.
Bye-bye.
Have a good day. Vivian, have a great day.
Thank you. Thank you all.
Okay. Bye.
Okay. Bye-bye.